So for those of you that don't know me, my name is Ryan, and I actually did my PhD or NhD here at UCL under the supervision of Professor Ezat Aweze. And what we were looking at is this new kind of modulation scene called SEFDM, which stands for Spectrally Efficient Frequency Division Multiplexing. And further to what John said before, that these kind of seams, new seams, are kind of dealt with at the beginning with excitement. A lot of people also take it with a pinch of salt because you're trying to kind of challenge traditional barriers, and that's where things start to go wrong. So before I continue, how many people here know about OFDM? Okay, and how many people here know where OFDM is used? Okay, about 50-50. Okay, so I'll just do a small kind of snapshot. So OFDM, orthogonal frequency division multiplexing, is used in current 4G systems. LT, is it 4G? 3.95G, whatever you want to call it. So OFDM is classified as, well, it is actually used as a technology enabler in current communication systems. However, it's got a long-standing history. The first practical applications could probably be traced back to 1995 with digital video broadcasting. Then broadband communications, ADSL, that uses OFDM. Certain Wi-Fi standards use OFDM. And in actual fact, certain other non-wireless SIMs like power line communications also use OFDM. However, the theoretical concepts can be traced way before that, back to the 1960s, by a person called Chang, who actually wrote a paper on parallel data transmission, which at that time and age was considered wacky because it was way too complex to do. And then a few years later, another guy called Weinstein actually kind of continued his paper, but he proposed the use of the DFT to actually implement that parallel data transmission. And what actually made OFDM feasible is probably something everyone hopefully knows, called the FFT, which kind of scales well with system size, whereas the traditional bank of modulators doesn't. And that's probably one of the key technologies that allowed systems like OFDM and likewise that use the FFT to actually be implemented in practice. As you probably know or probably heard of, there's usually quite a long span between theory and application. So CDMA, which is used for 3G systems, spectrum technology can be traced back to probably the 1940s. Secret communication systems by an actress called Hedy and a pianist called George, and they kind of not invented, but they were part of the invention of like frequency hopping, and then frequency hopping is used as one of the spectrum standards. Now, OFDM is kind of the reciprocal of what CDMA is. So in CDMA, for those of you that do know how it uses, you get a slow-moving signal at a low data rate. You multiply it by a high data rate code, and then you kind of spread the signal in the frequency. So a narrowband data signal in the time domain becomes a broadband signal in the frequency domain, and that's how CDMA and 3G systems work. OFDM is actually the opposite, so you've got a high-speed data rate in the time domain, and you make it into a low-speed data rate, again, in the time domain. So in the frequency domain, what you've got is narrowband. So anyone know here why we use frequency division multiplexing instead of single carrier SIMs? So we use frequency division multiplexing to basically counteract the effects of multipath fading. So if you consider you've got a channel and you've got nulls in the channel, like multipath fading. If you've got a single carrier system with a single bandwidth, if you've got a null there, then you wipe out the signal. With frequency division multiplexing, you've got multiple narrowband subcarriers, which means that even if you take out one of those subcarriers, you can still recover the signal. So what's good about OFDM? So OFDM is, again, a frequency division multiplexing scene. But what you're doing, you're maximizing the available bandwidth you have. So and you do that by overlapping the subcarriers. So if you consider I'll just plot it here. A standard FDM system where you've got carriers like that narrowband, in OFDM, you actually overlap them. So therefore, the bandwidth that OFDM takes compared to a standard FDM is a lot lower. However, for this to actually apply, though, there's something called the orthogonality rule, which kind of specifies that the frequency spacing between two adjacent subcarriers has to equal the width of its subcarrier from the center of that carrier until the first null point here on the time axis. So the equation very briefly is delta f times t equals 1, where delta f is the frequency spacing between adjacent subcarriers, and t is the symbol period of one OFDM symbol. Now, I said before that what we do is slow the data rate, and this is done by a serial to parallel converter. Those of you that do digital electronics will understand that if you've got a high data rate signal coming in, and then you've got multiple lower data rate signals coming out, obviously if you've got 100 megabits here, then there will be a 25 megabit OFDM symbol at the output here. Okay? I'm doing all this preempt because otherwise, if we don't kind of go through these basic stuff, then SEFDM and all the other carriers, multi-carrier systems will not make any sense at all. Not only that, it's actually because we actually violate this equation deliberately to actually achieve what it is we want to achieve. So that, in a nutshell, is what OFDM is about. And now, if we move on to the actual presentation, hopefully things will start to make more sense. So, just a brief agenda. First, we'll start with the concepts of like time frequency packing, which in some ways can be translated as non-orthogonal multi-carrier schemes. Then we'll talk more about the system that we developed here at UCL called SEFDM, talk about the transceiver, the transmitter and the detector. Then we'll talk about some of the test beds that we've built, both for wireless and optical, and then we'll wrap up with conclusions to move on to the next presentation. So, the two first presentations in the morning by both John and Misha talked about 21st century trends. We want more, and pay nothing for it, pretty much. So you've got more devices, you want more data rates, you want to be more mobile. You actually want to get coverage and be able to use the phone if you travel on the train from London to Cambridge, which at the moment is not the case. So therefore, we're constantly thinking of new ways of how to improve stuff, whether it's at the network, whether it's at the application layer, whether it's at the physical layer. And this particular presentation and SEFDM target the physical layer. So, you've got everything before it, everything after it, what happens in between. So the actual link, which can be wireless, optical, copper, or so on and so forth. So what is the aim of these new type of modulation schemes we're talking about? Well, what we're trying to do is essentially squeeze more data in the same bandwidth. So you can see this from different perspectives. You can either have the same data in less bandwidth or more data in the same bandwidth compared to an OFDM system. And also some new techniques, new techniques, but old techniques which are now being applied into multi-carrier systems like pulse shaping. And I suppose the key difference here is some novel detector schemes like sphere decoding, which again is probably still not mature enough in terms of like the silicon technology being able to implement it, but nevertheless it is doable compared to what it was 20 years ago. And this is just some of the other research going on around the world. It's by no means exhaustive. It's just an indication of some of the groups we've actually worked with too. So as I said, we've got SEFDM here at UCL. At Lund University in Sweden, we've got FAST and the Nyquist. Parma University, they applied the time frequency concept in the optical domain, and they call it actually time frequency packing. And then here at UCL in the optical domain, they use fast FDM, which is a special case of SEFDM for the optical domain again. Matsumoto, who's Japanese but is actually affiliated with the University of Oulu in Finland, he developed a system toward the end of 1990s, early 2000s called FOMS, Frequency Overlap Multi-Carrier System, but now he's kind of renamed it into NOFDM, which stands for Non-Orthogonal FDM. Gerhard Fitwes, in addition to the tactile internet and the cooperative multi-point systems he's done, he's also actually working on the physical layer too at Dresden University, and something called GFDM, which stands for Generalized Frequency Division Multiplexing, and OFDM is a special case of GFDM. So you can probably start to see how all these things come together. And some of the major EU projects that are taking place is one is called 5G Now, and the other one is called METIS, and they deal with non-orthogonal waveforms. So far, so good? People not sleeping yet? Yeah, not running out the doors? Okay, that's good. Who here thinks that so far, so good? Who thinks it's a complete disaster? None of the two? Okay, that's fine. Probably sleeping. Probably that blood in the stomach now digesting. So this is just a timeline of non-orthogonal techniques. The actual theory behind it, in particular to pulse shapes, is can be traced back to 1945 with Gabor, who kind of did a very good mathematical analysis of orthogonal pulses versus non-orthogonal pulses, and what the time frequency characteristics were for different pulses. One of the key papers was by Mazur in 1975, who actually defined faster than Nyquist, in other words, kind of violating the Nyquist scheme and transmitting data at higher speed. We'll talk about that in a second in forthcoming slides. And then moving along, you can see the blue line is kind of like the mobile communication systems every 10 years, as Misha alluded to earlier on. And now we're kind of here into the 5G unknown domain. So, what is SEFDM? Well, essentially, if you understand OFDM, then SEFDM is basically a compressed version of OFDM. So we kind of have the same number of carriers, but we bring them closer together. And if you see that on the time frequency axis there, what we're trying to do is fit more symbols within the same bandwidth as you would have in an OFDM system. Obviously, one thing you'll see here is at the peak of each subcarrier in OFDM, all the other subcarriers are null. That's not the case in SEFDM. Yeah, you get interference here. So once you get interference, self-created interference, that means you need to come up with new techniques to kind of mitigate that interference. And this is where most of the research is taking place. Just a very brief comparison and animation, again, of SEFDM versus OFDM. The orthogonality rule discussed before here about delta F times T equals 1. We actually deliberately violating SEFDM by basically squeezing the subcarriers closer together. So the width, the data rate is exactly the same, but the frequency spacing between each subcarrier is less. So therefore, as a result of that, we get self-created interference. Okay? So what I just described now about SEFDM is working in the frequency domain. But frequency domain and time domain are reciprocal. So FTM is actually the reciprocal of SEFDM in some ways. So whereas in SEFDM we reduce this in order to squeeze more data in the same bandwidth, in FDM we kind of expand this to fill more data in the same bandwidth. Okay, so reciprocal things. So this is the scheme that they're working on at London University, with whom we actually have close links. And this proceedings here is quite recent, so it kind of lay dormant for quite a few years, and now all of a sudden they decided that FDM is actually quite a promising technique for 5G systems. And this is what I talked about before about Mazur, who actually wrote the first paper, or to the best of our knowledge, wrote the first paper on faster than Nyquist signaling, which again in turn is actually a subset of another scheme called partial response signaling. And what Mazur actually found is that you could actually squeeze more data beyond the Nyquist limits without degrading bit error rate performance. So you think, well, how the hell can you do this? You know, if things start becoming non-orthogonal and you're violating principles, how can you actually achieve the same bit error rate? Well, what he found, and if you read that paper, which I won't go through now, he found that there's actually two different things here, which although may seem correlated or dependent on one another, in actual fact, you can actually adjust one without influencing the other. So what he found is, one thing is the orthogonality, which is this rule here we defined before, the symbol period times the frequency spacing equals 1. The other thing is the Euclidean distance between the pulses. So if you're thinking about the Cartesian axis and the vectors, and you've got the Euclidean distance between different points, you want to compute the distance between those points. And when you come to compute the bit error rate, and recover the bits, what you're doing is, when you've got all the noise, so if you think about QPSK, for example, and then with noise it becomes something like this, what you're doing is computing the distances between the soft point that you received and the ideal point, and trying to figure out what point is actually the correct one. And that's what we term by Euclidean distance. And what you found is, like, for example, binary pulses, the Euclidean distance is 2. Yeah, that's the minimum Euclidean distance. And what you found is when you actually squeeze this, so when delta F times T is smaller than 1, the minimum distance actually still remained 2, which means that the bit error rate would not change, because you're actually not affecting that minimum distance between the pulses. And they squeezed it more and more and more, and he found that the cutoff is 0.802T. So if you were to bring this to 0.802T, you could recover, you could achieve exactly the same bit error rate as you would do in the standard orthogonal scene. It does imply something, but we'll come on to that in a bit. But this was for sync pulses, this limit here, which, as you probably very well know, cannot be achieved in practice because of infinite length, and in practice we can only do finite length. So this is where some other people, this was by Liveris and Georgiadis in 2003, wrote another very good paper called Exploiting Faster Than Nyquist Signaling. And they used root-raised cosine filters to see if they could improve upon the bandwidth that sync pulses would get. And they found that they could actually squeeze it for a 30% roll-off. They could go down to about 0.703, which translates basically to an increase in about 40%. So where if you have, for example, 4 crown, that's 2 bits per symbol. If you have an extra 40%, then it's almost 3 bits per symbol. Okay? Yeah, 3 bits per symbol. So the question comes along, everyone says, well, why are you violating sinus capacity? And we're like, no, we're not doing that. Sinus capacity assumes that you're using sync pulses and assumes that everything is linear. So what we're actually saying here is, well, no, for practical pulses like the root-raised cosine pulses, you can actually exploit what's called the excess bandwidth, which I'll not go into details. And by doing so, you can actually squeeze more bits within the same bandwidth for practical situations. If you had it in theory, from a theoretical perspective, sync is the best you can do, yeah? So you've got a nice rectangular pulse and you've got infinite bandwidth. But in practice, you cannot achieve this. So this is where it seems like SEFDM and FDM consider the situation from a practical perspective. Okay? Still with me? Okay, not lost, not run away, okay. So moving on to now to the signal generation and detection for SEFDM. So the I50, the FFD are orthogonal. Yeah, everything's orthogonal between them. And we're using it to do something non-orthogonal. How do we do that? Well, we do a bit of kind of like smart configuration here. We're playing around with multiple I50s, do a bit of phase rotation at the input and the output. If you do phase rotation, not complex multiplications, that means you're not actually increasing the complexity, which means you can actually use standard I50 blocks to do non-orthogonal SEFDM with a complexity which kind of scales in the same way as a standard OFDM system would do. Obviously, there are drawbacks with this system in terms of the number of I50s that you have depends on the bandwidth compression you want to achieve. So we've got a term in SEFDM which you may have saw earlier called alpha. So in SEFDM, this product here is called alpha, where if alpha equals 1, it's OFDM. If it's less than 1, it's SEFDM. And in this case, you play around with alpha. So you could say alpha equals 0.8. Okay, what if we have it as a ratio? So let's say that alpha equals 4/5. How do we relate alpha equals 4/5 to this picture? The way we relate it is that the denominator actually relates to the number of I50 blocks you need. And then the numerator relates to how you actually position the data symbols across these I50s. More details are in the papers. This is just to give you an idea of how you can actually use orthogonal I50 blocks to generate non-orthogonal signals. So we did all the theory, hunky-dory. We think, well, can we actually implement this in practice? And that's where all hell breaks loose. So one of my colleagues, Marcus, actually did implement this specific transmitter you saw. We've done like 3 different transmitters. This is the one that we found was better suited for hardware implementation. The reason being that we used FPGAs, and FPGAs are well suited for parallel architectures. So that's why we implemented that specific transmitter you saw on the previous page. So we found that, yes, it is doable to implement this in practice. And this is the signal generator part. And this is actually the hardware that I used for it. At the time that this was built, I think 2008, 2009, it was state of the art. It had 16-bit DAX ADCs, which at the time was state of the art. Nowadays, probably you can get it off the market, off the shelf. But at the time, he actually built all this. So Marcus even populated all the boards with resistors and everything. So quite an achievement for the time. And then he went on to actually implement the system right in VHDL. This is the layout of how it looks in, we're moving on now. So this is the VLSI. So then the other colleague, Paul Watmo, he did the VLSI aspect, and he actually designed it using a 32 nanometer CMOS process. And that's how the layout would look on the chip if we actually went over to actually fabricate it afterwards. And then here's just a comparison of OFDM, where alpha equals 1, compared to alpha being 2/3 or like 0.5. And when alpha equals 0.5, that equates to the fast OFDM technique you saw right at the beginning of this presentation, which is currently being used in the optical domain. Okay. Just go and catch your breath. Everyone all right so far? Okay. Anyone sleeping? Okay, that's good. Okay, so this is just again, I suppose, a summary of what we've discussed so far of basically you trading off bandwidth savings for intercarrier interference. So the more you squeeze the subcarriers closer together, the more bandwidth efficient it becomes at the expense of more self-created interference. And just like with every system and everything in this world, there's always a trade-off. You increase one thing, you lose another. If you do find a way around this, then please do let me know. So we talked about transmitter, we achieved the transmitter, we designed it, we implemented it. So what happens at the receiver? We actually have to get those symbols back. And what happens with this self-created intercarrier interference you get? Well, this is what I was alluding to earlier on, where if you use maximum likelihood, that is the optimum detector. And what Maslow did back in 1975, where you could recover and achieve the same bit error rate by squeezing the data closer together, was doable, provided that you use the optimum detector, which is maximum likelihood. Now, does anyone, who here doesn't know what maximum likelihood is? Who knows what it is? So you don't know, you may know, you may not know. Okay, that's fine. All right. So maximum likelihood is basically, it tests for every single possible sequence. So if you imagine that you've got 4 bits, you've got 2 to the power of 4, 16 possible combinations. And you want to, at the receiver, find out which combination was actually sent. Well, maximum likelihood tests the Euclidean distance, so it finds Euclidean distance for all possible combinations between the received symbol and what the possible combinations are, the entire set, and picks the one with the smallest, shortest Euclidean distance. Okay? So if you've got like 4 bits, 2 to the power 4, 16 combinations, it's great. What happens if you've got 4 QAM, for example, with 32 subcarriers? So you've got 4 to the power of 32, or 2 to the power of 64 possible combinations. I'm talking about a few billions, trillions combinations, probably not doable, at least not in real time. You may wait a few years to get your symbols back, but you probably wouldn't get them in real time. So we thought, okay, maximum likelihood is not possible. What's the simplest solution? Well, simplest solution is zero forcing. So zero forcing is not new. It's an equalizer. It's used for channel equalization, where you invert the channel to basically kind of counteract what's happening in the multipath fading. So we thought, well, we've kind of got a channel here. If you consider the SEFDM self-created interference between the subcarriers, we can kind of visualize a channel matrix from it, which is deterministic. We can actually compute that. So we thought, okay, let's apply zero forcing, just invert the interference we've done. Great. There's something that happens in communication systems. You have noise. So what happens when you've got noise? Noise is amplified. So if you're inverting the noise, so if you've got 1 very small little noise, like 0, 10 to the minus 6 denominator, yeah? Very, very small. And then you invert that, what does that happen? 10 to the power of 6. So automatically, if you're expecting a value of 5, now you've got 5 times 10 to the power of 6. So it's not exactly the result you're expecting. So we found that zero forcing wasn't good either. So then we started considering schemes in between. And here we were inspired by the research taking place in MIMO systems, multiple input, multiple output antenna systems, where they've got similar issues with the actual MIMO channel matrix at the receiver. And they implemented a technique called sphere decoding. Now, the sphere decoding, its roots are actually another theory called lattice decoding, which can be traced back to the early 1990s. And what that does, it kind of constrains the solution of the maximum likelihood. So instead of saying search absolutely every single combination, what it does is it takes a first estimate, which in this case, for example, could be zero forcing or some other simple detection scheme. And then it says, right, okay, well, I think then that my solution is going to be somewhere around that first estimate. And it kind of draws a circle with a specific radius, and it says, I'm only going to test what's in that circle, which could be, probably just 20 combinations instead of 20 billion combinations, okay? So that's the concept of sphere decoding, which is still complex, but instead of being non-polynomial complexity, which is maximum likelihood, this is of a polynomial complexity. So we'll talk about that in the forthcoming slides. So this is just a snapshot of some of the detection schemes that we tried in SEFDM. Zero forcing, TSVD is again a linear detection scheme, but what it does, it improves upon zero forcing in terms of getting rid of the values in the matrix which would cause the noise to be amplified. So that's why it's called truncated. So when you've got the channel matrix and then you decompose it using singular value decomposition, you get certain singular values which kind of affect, if you've got an input and multiply it, what the output will be. You truncate those that are very small. And that did improve upon the performance of zero forcing. Iterative detection was, again, another thing we tried. Maximum likelihood was for only small system sizes, and was quickly found that it cannot be implemented in practice. And then sphere decoding, which we just discussed, and then a fixed sphere decoding, which fixes the complexity of sphere decoding, and I'll talk about that in a bit. And then we tried a number of different hybrid schemes. So this is just a visualization of what sphere decoding is, a very simple visualization. So if you can imagine that this is, 32 QAM. So this is 32 QAM, and your first estimate is here. So you say, this is the center of my circle. And then you've got a radius, and instead of saying, what maximum likelihood would do is like, okay, I'm going to test my point from here, and I'm going to examine the Euclidean distance across all these points. What sphere decoding says, well, no, actually, I'm not going to do that. I think that this is a very good first estimate, therefore, I'm only going to test its nearest neighbors. Obviously, people have written entire PhDs on what the radius should be. So I'm not even going to try and tell you what the radius is going to be, okay? Because my PhD wasn't on just the radius, it was this entire system. But hopefully you understand the concept of what sphere decoding is. Okay, so it kind of constrains the solution of maximum likelihood. However, if you do pick the radius to be large enough to encapsulate the possible solutions, then you will achieve the optimum bit error rate, as maximum likelihood does. Okay? So this is, if you were then to actually run the algorithm in practice, this is how you would kind of implement it. So you start at the root of a tree. You can visualize sphere decoding as a tree. And then you're saying, right, I'm starting at the root, which is my original estimate, the first estimate, which probably doesn't work very well. And then you start computing Euclidean distances. So you think, okay, I know this looks like exactly the same, but they're not. Okay, so this distance is probably, well, it will be smaller than this distance. Okay, so you're computing Euclidean distances, and you always pick the one that's minimum. And then you say, okay, between this and this point, I'm going to select this node. You come here, then you say between this node and this node, this is sorted, I'm going to pick this node. And then eventually you come with a solution. Obviously, this is a very simple architecture because this is BPSK, -1 + 1, with only 4 carriers. So if you scale that up, you can imagine how many nodes you would have at each level. Okay, but that is the concept of sphere decoding. Now, the problem with sphere decoding is it depends on the noise in the system, AWGIN, additive white gaussian noise, as well as the self-created interference. So depending on the channel conditions and the noise, the time it takes to converge to a solution varies a lot. Obviously, when you do increase the SNR, that variable complexity reduces, but still, this is what you see at each point is the complexity required to decode the same symbols in different channel conditions. Well, if you come to implement it in practice, you can't say variable complexity, especially on FPGA. You need to account for the worst case scenario. Well, you can see here this is not really efficient, yeah? If the worst case scenario is this, but most of the time we're getting this, then you're not really making good use of the FPGA. In addition to the fact that on an FPGA, you may not be able to achieve this. Maybe the complexity of the iterations in the algorithm is so high where you probably couldn't fit this on the device. Okay, so we thought, right, we don't want variable complexity, we want to fix the complexity. So this is where we then consider the fixed field decoder. This is a hybrid version. So here, TSVD FSD is the first estimate, which we discussed before at the center, would be the output of the TSVD detector, which we then feed into the fixed field decoder. And then what the fixed field decoder says, right, at each level of the tree, I'm only going to examine 2 nodes. Okay, so no matter whether you're here or whether you're 10,000 levels below, you're only going to take the 2 best nodes. What's the drawback of that? Degradation in bit array performance, yeah? Because what you're saying is, I'm going to choose the best 2 nodes, but that's not necessarily going to take you onto the best path, because you're no longer examining complete solutions all to the end. You're examining the best solutions at each level, which may mean that at one level you may choose a node that will not eventually lead to the optimal solution, but it will lead to a suboptimal solution. Okay, so this is why, again, you've got a trade-off. We're saying, like, I want a fixed complexity, I want an algorithm that will work in real time, which I can actually implement on the FPGA, but I will have a trade-off a bit of SNR to achieve the same bit error rate. Okay? So that's fixed field decoder. Hopefully I haven't lost you yet. I'm trying to make this as simple as possible. So this is the FPGA platform we used. So in the first version, what we did is we implemented the linear detector, zero forcing and TSVD, on an FPGA, which is the left-hand side. And then we implemented the fixed field decoder on a digital signal processor on the right-hand side. And if the question is, well, why did you do that? The answer is because the fixed field decoder, even the fixed field decoder, was too complex at the time to implement on the FPGA, which in this case was a Vertex 5. So therefore, we use this joint FPGA DSP environment to be able to implement the receiver, and then we did all the analysis in MATLAB. Okay? Again, talking about optimization, we thought, right, okay, so the fixed field decoder is still too complex. How the hell do we optimize this further down the line? So we thought, okay, so what is the bottleneck in fixed field decoding? So we thought, what's the sorting stage? Again, this is a simplified version. You can only see 2 nodes. What if you had 50 nodes at each level? Well, there's a lot of sorting taking place. So we thought, right, okay, fair enough. What if we get rid of the sorting stage? So if we just remove the sorting stage completely and we just say, we'll pick the 50 at that point and then the 50 at the other point, and basically you're creating independent paths. Again, same trade-off. You get simplified algorithm that works faster, but at the expense of degraded bit error rate. So we thought, okay, so can we improve the bit error rate in any way? And we thought, yes, we could. And how do we do that? Use a technique called modified real value decomposition. So what does real value decomposition mean? It means you take a complex matrix and you decompose it into its real parts. And the way we did this originally, the original fixed field decoder, is first you examine all the real parts, then you take all the imaginary parts, and then you get the solution. So we thought, right, okay, instead of doing first all the real parts and then all the imaginary parts, what if we kind of permuted between the two, so do real imaginary, real imaginary, real imaginary, and we found that that did actually improve the results using the simplified sort-free version of the algorithm. So you can see here the ideal response is the green one, TSVD FSD, and the improved simplified algorithm by using the modified real value decomposition, the blue one, is almost quite close. So what we did there, the modified real value decomposition didn't have any additional complexity, so that was kind of like, a bonus mark. But the sort-free actually did simplify over the original fixed field decoder algorithm. So this is an example of how we were able to basically simplify the algorithm without degrading the bit error rate by using other novel schemes with the algorithm. So kind of algorithm optimization, if you like. Okay? And talking about implementation, because, okay, we did a transmitter, we did a receiver, but we hadn't actually implemented the sphere decoding on the FPGA. We really wanted to see, you know, what kind of complexity, circuit complexity that would take up. So we decided, okay, that's the next stage. And this is the part here in the dotted boxes that we actually implemented on the FPGA in isolation. And this is the results we got. And you would think like, okay, the sorting stage is actually that complex. Well, the results speak for themselves. So here it's, my colleague Tong Yang did this, so I'm just trying to make sure I say the right things here. Right, okay, so within FPGA, for those of you that know more about the digital electronics, you've either got a fully parallel architecture, which means that on each clock cycle you carry out the entire algorithm, or you've got a fully pipeline architecture, which means that you minimize the area but you increase the latency, or you've got something in between. And this is what we've got here. We've got something in between, so we've got kind of a semi-parallel architecture. Now, the difference between these two, the second and the third column of that table, is the second column is the sort-free algorithm without the sorting stage. And the third column is, well, here it's called modified non-sort-free, but it's basically the one we actually carry out sorting. We can see here that there's a reduction of 8 times in speed if you use the sorting stage. And then in terms of performance, if you used it in its purity without the modified real value decomposition, you can see here there's almost like a 2 decibel degradation in bit error rate performance. So this is like with the sorting stage at this speed, or without the sorting stage at that speed. So again, trading off speed with complexity. And this is how it looks on this was the next device we used, the Vertex 6, I used the Vertex 5, and this is the layout just for the implementation of the fixed sphere decoding. Not the receiver, not the FFT, not the linear detector, just the sphere decoding itself. So it takes up quite a bit of area there, you'd imagine, yeah? So probably not ideal. So then we explored other more novel schemes. And this one was iterative detection, as we did before. But in this case, we actually used soft inputs. So basically, we kind of played around more with the constellation diagram. And we found, like, okay, if we kind of play around with this area for each point, can we achieve better performance? And the answer is, yeah, yes, we can achieve better performance at a complexity which is a lot lower compared to the standard at the time being TSVD and FSD. So the first two figures on the left-hand side compare iterative detection to TSVD as well as the hybrid version. And then here you can see the complexity. So I think the most relevant one here would be this one. So you can see here that in terms of bit rate performance, they're almost the same. However, the tree width, which defines the complexity for the fixed sphere decoder, for the iterative detection was 16. For the TSVD version was 1024. So, you know, almost an order of magnitude more complex, okay, for the same bit error rate. So again, another example of how when you continue optimizations and try out different methods, you kind of trying to improve the trade-offs between error rate and complexity. So this is kind of the point where we kind of reached a big wall. We couldn't really improve upon that. So we thought, okay, well, what can we do now? Do we just like dump it away and think like, this is rubbish, forget about it, let's go and do something different. I don't know, Internet of Things, for example. So we thought, no, okay, let's give it another go. And what we thought is like, okay, so at the moment we've considered everything adjacent, all the carriers together, not really playing around with them. What if we start consider them in blocks, so kind of creating bands of subcarriers? Can we improve upon the performance? So we thought, well, yes, we can. So if every, say, 8 subcarriers, we null a subcarrier and then continue it, so you've got bands now of 8 subcarriers, The actual true complexity is probably only for 8 carriers. So even if you've got 128 carriers, the actual complexity is still only for 8 carriers because of that null subcarrier you've got in between, you've created a band, which means you've really minimized the interference between the other blocks. And here is the effective bandwidth compression. So whereas the frequency space in between the subcarriers is 0.582 or 0.761, in actual fact is probably a bit higher due to the fact that you've actually now got dead space in between the bands. However, you can support a lot more subcarriers. So here in this case 128, which for a typical conventional SEFDM system, you could not do this. At least not using the current detectors that we did. And this is the experimental result. So here the actual amplitude is exactly the same. We've kind of just shifted it just for illustration purposes. And the bandwidth you can see here actually relates to an LTE standard, but the number of subcarriers in between do not. So an LTE standard's got 601 subcarriers. Here we're only trying 128. And the reason we want to do that is just to compare basically OFDM to SEFDM. Okay? I'm going to speed up a bit now because I'm a bit conscious of time. So this is what we call as the block area detector, which uses the same detector we discussed just before, the iterative detection with soft decoding. And what we found here is that for a much higher number of subcarriers, 128, this is the conventional SEFDM, this is the block SEFDM. So you can improve it by 4.5 decibels for the same effective bandwidth compression. So all this has been done without any error control. So no convolution codes, no turbo codes, no nothing. Okay, it's just pure raw data basically. So that's the next stage now where we start introducing error control. So here we've got convolutional encoder and decoder along with turbo equalization. And this is kind of like the original part, if you like. The other stuff is kind of standard. You can find it in any kind of communication system using convolution encoding and turbo equalization. This is kind of the extra thing we've added here in terms of the SEFDM part to ensure you generate those non-orthogonal signals that we discussed earlier on. And here are the results we get. And as you probably know, with convolution encoding and stuff, you've also got iterations. As you increase the iterations, you improve the result. But after some point, you don't get any further improvements. So here you've got for V4 and V20, it's the same thing. So obviously you don't want to do 20 iterations if you can get away with doing 4 iterations. And obviously here you can see that the compression is actually quite high, alpha equals 0.6. Beforehand, we said like, you can go to alpha equals 0.8 in theory. Here you can do 0.6, obviously using the error control. And now to wrap up, we'll just quickly talk about the test beds. We roughly done 2 test beds. One was the wireless, one was the optical. For the wireless, we try to emulate LTE as much as possible. I say emulate because it's an LTE-like experimental test bed. As I mentioned earlier, we didn't actually use the exact standard in terms of subcarriers, but we did adopt it in terms of like the bandwidth allocated to LTE. Oops, going a bit fast there. So that's the test bed that we set up in the Aeroflex lab on the 10th floor, if you ever get a chance to see it. So then you've got the channel emulator and the PXI, which kind of generates the SEFDM signals. And then at the, you can't see it here, but you've also got a digitizer, which receives the signals that have undergone noise and multipath fading. And then we do the analysis in MATLAB. These are the parameters. Again, I don't want to dwell on this too much, but you can just see how in OFDM you've got the phase rotation there, which happens here. You've got this bubble, and this is due to the self-created interference created in SEFDM. And you can see here, obviously, the detection of OFDM is a lot better compared to SEFDM due to the fact that you don't have that self-created interference ICI in OFDM. Okay. This is a snapshot of the time frame we use. So you can see this resembles one for an LTE standard, but it's been adjusted for SEFDM. And here's when we try to transmit a picture. This is not my picture, by the way. That's my colleague Tong Yang for this picture. And so you've got the original in the top left there, nice and clear. And then as you kind of squeeze the subcarriers closer together, you can see artifacts building up. But still, you can recover it at what is considered a typical EB over N naught of 25 decibels. Okay? Results, performance analysis. This is a PAPR showing, like, the peak to power ratio is similar for both OFDM and SEFDM. Here we use the turbo decoding I described in the previous slide to detect the signals. And the two figures on the left just show basically the trade-off between throughput and bit error rate accordingly. Okay. Carrier aggregation. So this was the second part of the LTE testbed. So again, the same thing, but as you've got carrier aggregation LTE, we try to apply it for SEFDM. And what you can see here is basically you can fit another 2 component carriers within the same bandwidth that would be allocated to OFDM. And this is just the parameters used to set up the testbed. And you can see here, like with the multipath fading, the signal is quite heavily distorted. Despite that, though, we can still get very good performance results. So obviously, we've got a much larger x-axis now from 0 to 25 decibels instead of like the 0 to 10 decibels. But what you can see here is what we discussed before about the increase in spectral efficiency. So whereas the typical OFDM is 1 bit per hertz, you can increase it to 1.4 bit per hertz if you have an alpha of 0.72. Now, the reason it's almost 40% higher is because the actual increase in spectral efficiency is not 1 minus alpha, it's 1 of the alpha. If you were to do the calculations, you would understand why it's 1 of the alpha. So here we got about 38% increase in performance for the same SNR. And this is the optical, the results from the optical experiments we did. And what you can see here, again, it's kind of a twofold benefit advantage here. From one perspective, you reducing the guard band, and then you're reducing the actual bandwidth for the actual useful data compared to an OFDM system. That's the test beds. This is 2 kind of different scenarios we tested. So back to back, where you get rid of the fiber and just connect the optical transmitter and receiver together, and then one with an 80-kilometer fiber between. And we can see that this is the 8 QAM results for OFDM. And you can see that in both cases, NSCFDM with alpha equals 0.7 outperforms the 8 QAM in terms of achieving the same bit error rate at low SNR. And this basically is, we try 2 different ways. So what you saw before was direct detection. This is for coherent detection. And again, you can see the improvements achieved with SEFDM. So conclusions, just to wrap up. So what does this whole non-orthogonal time frequency backing, whatever you want to call it, do? It allows us essentially to work in new areas of the time frequency plane. So if you think about Shannon capacity, which you've probably learned from your comms, hopefully, where you've got the capacity curve, and 4 QAM is there, and 8 PSK is there, and 16 QAM is there. We are trying to work in these areas, basically, which were previously unexplored. And that, in a nutshell, is SEFDM. Thank you for your attention.